Thank you, Jan, for the introduction, and thank to all of you for having me here and for being here, sacrificing your lunch probably. Yes, so I'm Alessio, and I work as a senior lecturer at NDU in the field of software engineering, model-based software engineering, more precisely. And the title of this talk is the one that you can see in the picture. And as I wrote in the abstract, mostly I will try to talk a little bit about some research results that we obtain within two collaborative research projects. One is a national Swedish project, and another one is an European research project. Both of them involved business partners, international business partners, such as Volvo, Trucks, Saab, Bosch, and so on and so forth. And both of them were in the, field of automotive software, right? So just a little bit of background, which I think most of us in this meeting know, or at least experience, that the complexity and the size of automotive software systems have been increasing quite a lot in the last years, in the last decades. And there is this famous paper from Manfred Breu that actually tells us that already some years ago, the software system were containing gigabytes of software for several 100 million lines of code. And of course, now I guess it's even worse in a way. However, the size and the functional complexity of this system are only two, I would say, dimension of the complexity, because these systems, automotive software system, that comes with, we may say, a lot of or different non-functional or properties or qualities on the functionality of this system, such as, for instance, timing, right? So I think it's obvious that, or for us, it's pretty clear that automotive software systems, at least some functions of these systems, are real time. Let's think about airbag, for instance, or the anti-braking system, right? So for those functionality, it's not enough that we deliver the correct functionality from a functional perspective, but we also need to deliver them within a specified time interval that makes sense, right? So this is this added dimension of complexity is, of course, complicating also the development of this system. And on top, we have also standard like safety standard, ISO 26262, that dictates basically or oblige us engineers to adhere to, for instance, timing requirements. So given the complexity of this system and the importance of this, let's say, timing properties for the nature of the system, in those two projects that I led in the past years, we decided to try to basically improve the development of these systems. And what we noticed is that there were two clear trends, at least in the automotive domain. One was to use a sort of model-based engineering or approach, at least. But more precisely, we noticed that there were this tendency of using so technically it's called multi-paradigm modeling, but in short, it's like the use of different modeling or in general languages, so notation, that may be used at different level of abstraction. So each language may have a different abstraction itself. Most of these languages were formalized through metamodels, so with metamodeling techniques. And to some extent, there was also automation for interoperate these different languages. So, for instance, for producing or generating models starting from models defined with a language, starting from models defined with other languages, or generating code. So the usual setting of model-based engineering. But also we noticed that there was another trend that was, as we were mentioning, discussing before this seminar, the trend of having continuous integration, continuous delivery in general to aim for what is called DevOps, right? So deliver application and services at high velocity. So keeping in mind the idea of agility, but translating in a more let's say in a different domain, in a more safe and fixed domain. So what we did is we used or we took into account these two, let's say, trends and techniques. And the first thing was to define basically a methodology, which we called moves. And in this journal paper, you can read all the details, technical details. Now I'm just gonna give you an overview. And if we try to simplify the methodology, the idea is that, as I said, we are using different modeling languages for a different level of abstraction and for different purposes. So in general, we have languages that may be more general and not containing perhaps all the properties, constraints, and so on that we may need for verification of certain qualities such as performance and timing, right? And this kind of information may be contained in other in models that are described or developed using other languages, and that usually they are developed in later stages. So the idea is that we would use automation, and in particular we borrow the idea of model transformation to move from these general models to more concrete models that in our case were containing timing properties and constraints, such that we could basically have timing verification on these models because they were containing all the information that we needed in order to having timing verification. And once we have this, the results of the timing verification, we would annotate back these results in a continuous sort of verification setting, the results of this this activity back to the original model. Okay, and the idea is that you can see here the multi-paradigm flavor, but also the DevOps, because as I said, we have this sort of continuous verification, and also the thing is that all these steps were actually automated. So the result is that while this, for instance, this verification was even traditionally already done, with our methodology, because all these steps were automatic, you could actually do this verification at early stages of the development, already when you have a rather, let's say, simple or functional model. You could basically launch the transformation and have this chain. So the idea is that you will get earlier feedback on whether or not your architecture would very likely meet or not meet the, in our case, the timing requirements. So you would save money in addressing the problems, right? So this is the general methodology that we define, and then in the two projects we actually instantiated this methodology, and in one project what we did is that we used STDL as a general language, and then Rubus as a concrete, more detailed language for timing verification. And in one project, we would actually have two different activities for the timing verification. One would be analytical, let's call it this way, timing verification, so meaning schedulability analysis, basically. And it would be this leg, right, with the, let's say, feedback loop that I just described before. And another leg of verification would be using traces that basically are files that contains result from either data, either from the simulation of the system or from actual running of the system, right? And then again, we will have this, regardless of the verification technique, we will still have this loop over here where we will get some analysis based on traces and then feedback the results on the original model. In the other project, we had an instantiation of the same methodology, but with at least one different language, which is AMALTHEA. And both AMALTHEA and STDL, for those of you working in the automotive domain, should be familiar because are very, yes, STDL, it's well known, and AMALTHEA is kind of taking over, or we can say complementing the efforts that AUTOSAR and STDL were doing when it comes with multi-core architecture. So now in the next slides and in the remaining part of this presentation, I will just mention very briefly how we practically implemented this instantiation of the methodology in our projects. But before, yes, I just add basically a more generic slide for discussing why in this basically project we had both two different kind of verification, timing verification. One that we called timing analysis, so schedulability analysis, and one that is trace-based. And the difference, timing analysis, schedulability analysis are pre-runtime, so meaning that you can do that already on architectural level. You don't have to have the system developed. So this is a good point, but the drawback is that they may carry a little bit of pessimism, and they need the estimation of some properties like worst case execution time that it may be budgeted from previous project, but for instance, the worst case, it needs to be simulated, and then you need again this part, the trace-based. And as I said, instead the trace-based, let's say, verification makes use of traces, which, as I said, are collected either from the simulation or running of the actual system, and they carry a little less pessimism, basically, because they actually check the actual behavior of our system rather than the worst case scenario, let's call it this way. So the first, let's say, now in the next slide I will talk about this leg. And just to give you a little bit of background of the technology involved, STDL, again, it's a very well-known and established architectural language within the automotive domain. It's rather complex and contains a lot of concept and for modeling different things related to automotive systems. So from the structural part, but also to, for instance, timing and other concerns such as dependability, verification, and so on and so forth. So in our project, we actually use concept for the modeling of the system model, so at design level, and also we borrow some concept for the verification validation basically package. This was one language, and the other language, it was a robust component model, which is also in common between the two projects. And the robust component model, it's actually a very, I would say, compact language notation that was developed, is developed by a Swedish company, Articus Systems, in Järfälla, and has been developed by them together with several research partners, including us from MDU, but also KTH. And it was, since the beginning, it was tailored for enabling schedulability analysis, right? So, as I said, it's very concise language and contains only the properties that we need to know and have at architectural level, so to enable this schedulability or pre-runtime analysis. And very shortly, with this language, you represent the automotive functionality as a connection of components. Each component has some properties such as worst case execution time, how it is triggered, the period, and so on and so forth. I won't go into the details of the language clearly, but if you are interested, you can read one of the publications that I use as a reference in this talk, and you will find all the details. So when in the first leg of the verification, we went, as I said, we interoperate STDL and RCM, and of course we also created this feedback loop. And this publication contained the details of what we did. But yeah, this image also sum up basically all the tool chain in a way that we created. So we use EATOP, which is a plugin Eclipse basically based tool for the modeling of STDL model, and we from this tool we use the XML representation of STDL model. And what we did is that we actually created in the RubuSize, which actually is the tool that manages it's the development environment basically for the Rubus component model. We created an import plugin, which basically would translate this model into internal representation of STDL models for the RubuSize, and then we will actually have a transformation plugin, which will actually transform the model and whatever it's contained in this STDL description into an equivalent description of with the RCM language. Of course, here this transformation is based on a research and conceptual mapping that we've developed, and you can read these mappings here. But the idea is that, again, based on those mapping, we have automation mechanism, and then on this model we can run timing analysis. So we will run the schedulability analysis. We will obtain a report, and this report will be basically annotated back to the two models for consistency. Okay, so in this model, this starting model over here will basically be augmented with the modeling elements that would collect the result of our timing verification activities. And then we tested this or we validated this this tool chain in a way on the break-by-wire use case that we, or a simplified break-by-wire use case that we got from Volvo, and this is the use case, although I won't go into the details. So for the trace part, it was more or less the same idea, but the difference is that we actually instead of doing the verification on using schedulability analysis, we would analyze the trace, so the information that we get from the simulation. So actually the architecture looks a little bit different because we don't have any transformation. We are only working on the STDL model. But what we will do is that we will parse this model, we will parse the trace, and then we wrote, actually, this was written in C#, a plugin that will check the whether basically the data collected from the execution will match will comply to the requirements that we modeled in the starting STDL and STDL model. And at the end, we will write again the results, so meaning we will annotate and expand the original STDL model. Again, we verified we demonstrated the tool chain with a different use case. This is a wiper functionality of a truck, and here we also had more constraints. In the previous use case, we only had one timing constraint. Here we have 3 different kind of constraints. Now I think I'm finishing my time, but anyhow, it's what I just wanted to say is that we also similarly to the STDL and RCM integration, we also instantiated the moves methodology into the AMALTHEA and RCM, let's say, integration. AMALTHEA is, as I said, it's a language that tries to complement AUTOSAR with for multi-core architecture, and the tool chain in this case would look like this. and we use the Eclipse again tool that's for managing the AMALTHEA model. And then we wrote a set of Java programs that basically would use some of the API that were defined in the AMALTHEA plugin, and then we'll just transform the original model into a robust component model and run timing analysis. And yes, we also verified this with the break-by-wire use case. So this was just to basically showcase a little bit what we did, and to make a point that some of the things that Haas as a researcher point out, like model-based engineering, agility, and so on, that sometimes are a little bit may seems like a buzzword in a way, but they can be implemented, and they can also be effective in helping companies in reducing, in our case, in reducing the cost associated to a late verification of automotive system with respect to timing in our case. So before actually opening to question, I just want to have a little bit of advertising, because the research that I presented is very much related to automotive, but me and of course the research groups I belong to, we actually also touch upon different areas which may be, for instance, interesting or relevant for some of you joining this meeting. So those are the areas, and I try to also put some example of research that we do. So please, if you actually have something interesting in this area or in automotive software development, do not hesitate to contact me or Jan. This is my email, and then thank you so much for the attention. I hope I wasn't too long, and now I'm ready for questions in case you have any.